There is a famous legend that when chess was first invented in India by an obscure and little-known mathematician, the game very soon became popular and widespread. The royal prince of India offered the inventor anything he wishes as a reward. The modest inventor asked for only a single grain of corn to be placed on the first square of the chessboard and double for each subsequent square. And there are 64 squares on the chessboard. The prince laughed at this very odd request, but ordered for his wish to be granted. However, there was a little snag when they started counting the number of grains of corn. The first few squares were fairly simple. 1 for the first square, 2 for the second, double that, 4, then 8, then 16, then 32. Very soon, they discovered there wasn't enough corn in the whole of India. We can calculate the exact number of grains on the chessboard simply by adding the number in each of the squares. Now, this can be represented by a sum, which we can write. The sum is equal to 1 for the first grain on the first square, plus 2 for the next square, plus 2 squared, which is 4 on the next square, plus 2 to the cube, which is 8 on the next square, plus etc., until we will come to the very last square, which will contain 2 to the exponent 63 number of grains. Now, if we take this equation and multiply both sides of this equation by 2, we will get 2 times s is equal to, and then we need to multiply each of the terms by 2, so we will get 2 times 1 equals 2, 2 times 2 equals 2 squared. This term multiplied by 2 will give us 2 cubed. This term times 2 will give us 2 to the 4, etc. 2 to the 62 times 2 will give us 2 to the 63, and the very last term, 2 to the 63 times 2, will give us 2 to the 64. So we have another slightly modified equation. If we now subtract the two equations, the top equation from the bottom equation, we will get 2s minus s, which equals to, well, the best way to subtract the two equations is to subtract all the corresponding terms. So we take 2 and subtract the corresponding term there, which will get 2 minus 1, plus 2 squared, and subtract the corresponding term there, which is 2, plus next one, which is 2 cubed, and subtract the corresponding term. And if we do this all the way, you will find that you will come to plus 2 to the 63, minus 2 to the 62, plus 2 to the 64, and the very last subtraction will be minus 2 to the 63. If you examine this very closely, you will find that all the terms in this equation here will cancel out except for the 2 terms. And this will cancel out with that one, and 2 squared will cancel out with minus 2 squared, etc., all the way until you will find that the only thing that will be left here will be 2 to the power of 64. So 2 to the 63, for example, will cancel out with minus 2 to the 63, and there'll be another one that corresponds to this. So the sum, 2s minus s, which equals s, will be 2 to the power of 64 minus 1. If we use now a computer to calculate this, we will find that it comes to this very enormous number. In fact, if we calculate this number of grains, you will find that it's enough to cover the entire surface of the Earth to a layer 2 centimeters thick. Now, let's have a look at another example of base 3 exponentiation. Suppose we take 3 to the exponent 2. 3 to the exponent 2 equals 3 times 3 equals 9. Now, what does it mean that 3 to the exponent 2 equals 9. Let's have a look at a mathematical model. Here, the basic unit is represented by a circle. Base 3 means there are 3 circles in a module. 3 to the exponent 2 means that each unit in the module triplicates itself to produce another module of 3, which results in a total of 9 circles. In our decimal system, we use base 10. If we now consider 10 to the exponent 2, or 10 squared, which equals 10 times 10, here each unit tenplicates itself to give a total of 100 units, which is very rapid growth indeed. A very useful model of exponentiation using powers of 10 is to consider exponentiation of time and space. I have a film which illustrates this. It is called The Powers of 10. So hold on to your seats. We're off on a power trip.
The picnic near the lakeside in Chicago is the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now, every 10 seconds, we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is a kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1,000,000 meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the sun, followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last, we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The two little satellite galaxies of our own are the clouds of Magellan. 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception.
So as you can see, the power of numbers can take you far in and far out. In the course of history, we have inherited a very rich and diverse culture based on proper understanding of numbers. Mathematics is the universal language of science, and the numbers we studied in this module form the basis of that language.